This is a copy of a science textbook from 1849. When it was first published, it was extremely popular and sold out within 2 months. It took 25 years to write, and the author was racing against death to finish it. The book is Cosmos by Alexander von Humboldt. Humboldt was an explorer of sorts and extremely influential back in the 1800s. Charles Darwin loved Humboldt's work and was inspired by it in pursuing his own scientific adventures. In fact, Darwin brought some of Humboldt's earlier writings with him on his voyage aboard the Beagle in the 1830s. Today, not many people know of Humboldt, but he was so respected years ago that he actually has more things named after him than potentially anyone else in history. I'm talking natural features like mountain ranges, rivers, and species. A more recent biography about him by Andrea Wolff is titled The Invention of Nature, because what he did was to bring a new perspective to thinking about the natural sciences as interconnected with each other, and looked upon nature as important to the human story too. Alexander von Humboldt also had a famous brother, Wilhelm, and he basically is credited with creating the modern university system. His idea was to unite research and teaching, and his model was first implemented at the University of Berlin in 1810. The goal of this book, Cosmos, was to present the entire natural world as a single interconnected system, unified by underlying laws rather than a collection of isolated facts. Humboldt set out to synthesize everything known at the time. Cosmos aimed to change how people saw nature, not as static or divinely fixed, but as dynamic and continuously shaped by physical forces and the environment. This is the first volume of Cosmos, and there are 5 volumes in total. Humboldt was 76 when he published this first version and died in 1859, halfway through writing the 5th volume. It was widely read by academics and the general public, and it was so sought after that publishers had a hard time keeping up with demand. Overseas shipments of the book were sometimes swiped up by other bookstores before they could arrive at their destination. Looking inside the book, though, this doesn't seem like the kind of thing that would ever be so popular today. First of all, the text is tiny, with even smaller footnotes that take up pages. And it's a kind of summary of all that Humboldt has come to know of and think about science. It flows seamlessly between topics with no clear delineation or chapters. This first volume covers planets, comets, the density and temperature of the Earth, magnetism, aurora borealis, earthquakes, volcanoes, climatology, and organic life. But it also covers philosophical ideas like the connection between the material and the ideal world, a chapter in which Humboldt loves referring to everything as either animate or inanimate, something that seemed pretty common in science books from this time. For this video, I'm going to flick through this copy of Cosmos and see what an all-knowing science book from 1849 actually knew. What did they get wrong or right, and what more have we learned on these topics since? One of Humboldt's most famous ideas appears repeatedly in Cosmos, which is that ascending mountains is like traveling from the equator toward the pole. The temperature gets colder in latitudes moving away from the equator, just like it does with altitude going up a mountain. And this change in altitude shapes vegetation in the same way as global climate. He says that a difference of elevation of about 267 feet corresponds to the difference of 1 degree of latitude, and says that the different climates are arranged in successive strata, one above the other. Life is governed by gradients, not fixed placement. This idea is now known as the Humboldtian altitudinal zonation of life, and is a foundation of modern ecology. Humboldt emphasized that the same species look radically different under different conditions, and he rejected the idea that organisms are scattered arbitrarily. He says that the development of vegetation is essentially connected to the distribution of temperature, variations in atmospheric pressure, direction of the winds, and the quantity of moisture contained in the air. This frames life as constrained by physics and geography rather than perfect placement. It sounds obvious to us now, but was quite insightful at the time, especially when creationism was more popular. Humboldt was open to a more dynamic view of life, believing that it is influenced by the environment. Humboldt had studied this idea himself while exploring mountains such as this one in the Venezuelan Andes, which is now named in his honor. There are also Humboldt Peaks in Colorado and Nevada, and a Mount Humboldt in New Zealand. Let's take a look at some of the physics included in this book. On page 70, Humboldt speaks of what he calls the most interesting results of modern astronomy, which was that observations pointed towards the existence of an ether. The attempt to bring into unison the results of observation and calculation has led to the adoption of the very probable hypothesis that there exists, dispersed in space, a vaporous substance capable of acting as a resisting medium. We no longer have this idea of an ether in modern physics, but Humboldt considered it necessary. To understand why, you have to put yourself into the mindset of a scientist in the 1800s. Every wave anyone had ever studied required a medium. Sound needs air, water waves need water, vibrations need a string or material. So when experiments like the Young double-slit experiment in 1801 showed that light behaved like a wave through interference and diffraction, it seemed obvious that it must be waving in something. Humboldt even refers back to ancient cosmology, quoting that ancient Greeks thought there was a translucent illuminated ether lying beyond the visible vault of the heavens. This isn't presented as outdated or mythological, but by basically saying, look how clever these ancient cosmologists were because they got it right. The idea of an ether solved several scientific problems. It gave light something to propagate through. It allowed forces to act continuously across space. Even Newton had been uneasy about gravity acting across empty space with nothing in between. But as the 1800s progressed, the ether started accumulating impossible properties. It had to be perfectly transparent, but also unimaginably stiff to carry high-frequency light waves. The breaking point came decades after Cosmos was published. In 1887, Michelson and Morley tried to detect Earth's motion through this ether by measuring tiny differences in the speed of light. If the ether existed, light traveling with Earth's motion should behave differently from light traveling sideways. But it didn't. The Michelson-Morley experiment disproved the existence of an ether and tore down a lot of this early physics. Einstein's theory of special relativity did not require an ether for light to travel through. Instead, it showed that physics works better when no preferred reference frame for light is assumed. Humboldt's instinct that space is not nothing survives today in the concept of fields. What disappears is the idea that this structure must behave like a material substance. Later in Cosmos, Humboldt turns to electricity. The language reveals that electricity was thought of as a fluid. The electric fluid, in a neutral condition, forms a kind of atmosphere, extending far beyond the mass of our atmosphere, and also later describes the electric medium as physically imponderable and consequently following our globe in its motion. They treated electricity like a fluid because it behaved like one. Leyden jars became known in 1746 as a way to store electricity in a jar physically, like filling a container. This book was written almost 50 years before electrons would be discovered. This fluid picture also helped explain a mystery Humboldt was interested in, meteors. Shooting stars glow at altitudes where the air is extremely thin. If friction with air is the cause, then why do they shine so brightly, so high up? An electrical atmosphere surrounding Earth offered an elegant solution. Humboldt describes how bodies moving rapidly through this medium could light up from electrical excitation. Bodies passing through it would thus be heated and in a state of incandescence by becoming electrified. What changed in this thinking was not a single experiment, but a slow collapse of the fluid metaphor. In 1897, J.J. Thomson showed that cathode rays were streams of particles. Electricity was no longer a continuous substance. It was a charge carried by discrete entities called electrons. Once electrons entered the picture, electric fluids became unnecessary. Electric fields replaced electric atmospheres. Meteor light could then be explained through the compression of air, its ionization, and the formation of glowing plasma high in the atmosphere. Even though he may not have been right about the meteor light, this approach reveals Humboldt's mindset of trying to find unifying processes or hidden forces across Earth and sky that could explain everything we see. This book claims to discuss the entire cosmos, but at the time it was written, they thought the Milky Way was the whole universe. Though on page 141, he mentions that according to John Herschel, there could be another Milky Way, almost at right angles, which is composed of nebulae rather than stars. It wasn't until about 70 years later that we learned there is much more in the universe than one or two galaxies. In the 1920s, astronomers were still debating whether the faint spiral smudges in the sky were nearby clouds or distant star systems. The breakthrough depended on work done by Henrietta Leavitt, who discovered a relationship between the brightness and period of Cepheid variable stars. Using her method, Edwin Hubble measured the distance to stars in the Andromeda Nebula and showed it lay far beyond the Milky Way. Sky surveys and the launch of space telescopes later revealed that our Milky Way is merely one of billions out there. Humboldt had some interesting ideas about the interior of the Earth. Earth does have its own internal heat. This drives volcanoes, plate tectonics, and geothermal energy. In 1849, all of this heat was thought to be the result of cooling, that it was entirely leftover heat from Earth's formation. Humboldt writes, "This heat is derived from the secular cooling of the globe and from the small portion of the primitive heat which is still being disengaged from the surface. And also, the loss experienced by the central heat must have been very considerable in the earliest epochs." This model dominated geology for most of the 1800s. Lord Kelvin even used it to calculate Earth's age, arriving at tens of millions of years. That estimate deeply troubled later biologists because evolution seemed to require far more time. The resolution came from an entirely different field. In 1896, radioactivity was discovered. Radioactive elements spontaneously release energy as they decay. Earth's interior contains uranium, thorium, and potassium, which are constantly releasing heat. A component of Earth's heat was from cooling, but we now think half is from radioactive decay. Thinking about this made me wonder when the primordial heat would all dissipate, but it seems like the answer is that we still have a few billion years worth of cooling left. Volcanic and plate tectonic activity will slow down as this inner heat cools, but the sun becoming a red giant will still be the problem we face first before worrying about the Earth becoming a cold rock. While he might not have known the full story of the Earth's heat, what Humboldt did get right is that the Earth is a dynamic thing. The fact it was cooling meant it was reshaping itself, and that mountains, volcanoes, and continents were not relics of a single creation event, but products of ongoing physical processes, acting over immense spans of time. Back at the start of this video, I mentioned that Darwin was inspired by Humboldt. Darwin called Humboldt the greatest scientific traveler who ever lived. Humboldt's way of seeing nature as an interconnected system shaped how Darwin observed the world. Rather than collecting facts in isolation, Darwin learned from Humboldt to look for patterns and relationships and gradual change across vast scales of space and time. When Cosmos was written, Darwin had not yet published his groundbreaking work on the origin of species. The common idea at the time was that each species preserves the same characteristics through successive generations. But Humboldt had noticed that there were hints of undeniable changes over time. He noticed succession of organic forms which have successively displaced and succeeded each other. And in the book he mentions the great problem of metamorphosis, probably referring to a work from 1790 called The Metamorphosis of Plants, which in it is argued that all parts of a plant are variations of a single fundamental form, the leaf, reshaped through growth, environment, and development. Humboldt was wondering how not just plants, but animals, landscapes, climates, and even human cultures arise through gradual transformation rather than sudden creation. Everything changed a decade later in 1859. Darwin introduced natural selection. Species were no longer fixed, they are temporary patterns in a moving system. In retrospect, Humboldt is standing at the edge of a conceptual cliff. He can see that life is not frozen, but he cannot yet see how that motion works without design or direction. Cosmos did not contain a theory of evolution, but it created the intellectual conditions that made On the Origin of Species possible. Humboldt rejected the idea of nature as static and emphasized transformation. He treated life as shaped by environment and circumstance, not fixed design. Darwin later wrote that Humboldt's work stirred up in me a burning zeal to contribute something of his own. Whilst Cosmos is interesting and influential, be warned that it's very dense and difficult to read. It sent me to sleep a couple times just trying to skim it. But Cosmos is free to read on Gutenberg Press, so I'll link it in the description. When writing Cosmos, Humboldt was constantly asking how things connect and trying to find patterns. That way of thinking is great for learning new ideas, and it's also why I like using this video's sponsor, Brilliant. Brilliant helps you excel in math and computer science with visual, interactive problem solving and personalized practice. It is not about memorizing formulas. Brilliant gives you the structure and the problems that help find connections between ideas and make those ideas click. With their interactive courses, you are constantly making decisions, testing your intuition, and adjusting your thinking. It feels much closer to how real scientific understanding actually forms. If you have a goal to build better learning habits this year, then Brilliant is a great option. It has motivating challenges and encouragement to keep you moving forward. If you want to try it out, you can learn for free on Brilliant for a full 30 days by going to brilliant.org/Tibees or scanning the QR code on screen or clicking the link in the description. Brilliant is also giving my viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything on the platform. Thanks to Brilliant, and thank you for watching this video. A special thanks to my Patreon supporters, and a shout out for today's Patreon cats of the day, Taiki and Hermes.